In this lab, we're going to look at an addition reaction to an alkene. We're going to add hydrogen bromide using aqueous hydrogen bromide or hydrobromic acid, and we're going to add it to 1-hexene. Now, the problem is the hexene is nonpolar, while the hydrogen bromide is in an aqueous solution. So one of the things we're going to do is we're going to look at something called a phase transfer catalyst that helps bridge the polar aqueous environment and the nonpolar environment. Then we're going to look at the potential products, and we're going to analyze those products using gas chromatography. And one of the things it's going to help us do is verify Markovnikov's rule, which has to do with the preferred regiochemistry of addition reactions under acidic conditions. Right? So we're going to do a lot, and really all of this, right? We've got 1, 2, 3, 4 points that should be expressed in your purpose. Okay, so here's our reaction, right? In this addition reaction, the alkene, 1-hexene, acts as a Lewis base, or in this case a Bronsted-Lowry base, because a hydrogen ion is involved, right? A Bronsted-Lowry base takes the hydrogen ion from the hydrogen bromide, right? Now, remember this is aqueous, and I really should, right? We know under aqueous conditions that hydrogen bromide is probably dissociated, and so this strongest available acid is probably water instead of the hydrogen bromide, right? Okay, and so we've got 2 potential paths. The question is, right, does this new hydrogen ion end up on the end carbon, making a secondary carbocation, or does it end up on the secondary carbon, making a primary carbocation? Right? In either case, the carbocation is going to act as the electrophile, right? The Lewis acid, which means the bromide ion will act as the nucleophile, or the Lewis base, right? And so in either case, right, whichever way it goes, the bromide ion then will come in as nucleophile to interact with the carbocation electrophile. Right? Bromide ion comes in as nucleophile to interact with the carbocation electrophile. Right? That creates that new bond in either species. Right? And so we have, right, what's our choice? If it goes the green path, we get 2 bromohexane. If it takes the red path, we have 1 bromohexane. Right? And so it's determining the relative ratio of those 2, right, that is determining the regiochemistry. Right? Which is the preferred product. So we talked about using something called a phase transfer catalyst. Right? So the phase transfer catalyst is this quaternary amine, right? Or this quaternary ammonium ion, right? With 3 really long hydrocarbon chains, right? In this case, it's a trioctyl with a methyl, right? There's our methyl, right? So even as a salt, right, this creates an ionic compound that can be soluble in a nonpolar solution. Right? And so if we can replace the chloride ion with a bromide ion, right, the phase transfer catalyst can carry our bromide ion into the nonpolar solvent to act as a nucleophile. So it ends up that the bromide compound of our catalyst is more soluble in the organic phase than is the chloride ion version of the compound, right? So it goes in as the chloride, but in that solution, it can create the bromide, and the bromide then can partition into the nonpolar solvent or phase. So here are our 2 potential products, right? The 2-bromohexane and the 1-bromohexane. And we can see that the biggest difference between them is their boiling points. And we also have, right, some unreacted material left, so we will have 1-hexene in the reaction mixture with a boiling point of 63, right? So these should be our 3 major components in the product mixture. Right? So we've got our 2 potential products and our unreacted starting material. Right? Let's put that in here. Right? Now the question is, how do we determine, whether these are there, right? And if they're there, how much of each, at least in terms of a relative amount? Well, one answer to that, with these molecules that are of similar size but different boiling point, is to use gas chromatography. So this is a layout of a typical gas chromatograph, right? So it's chromatography. So we're using differential mobility of the substance in a medium. And we need a mobile phase, which in gas chromatography is a gas like helium. And we need a stationary phase, which is a non-polar coating on this thin glass tube. Okay? And so, right, the gas is flowing through, it's split. So there's a reference loop, right, gas that's not carrying any sample. And then there's a sample loop where the separating column is with the coating. And so you inject the sample into the sample loop through the sample injector using a micropipette, right? It goes through, and we'll talk about how the separation occurs, and then it comes out, and then the detector compares what's coming out of the sample loop to what's coming out of the reference loop, right? And it converts that comparison into a signal, and we can see some kind of output. Here's a picture of a gas chromatograph like the one we have. It is an HP for Hewlett-Packard 5890, right? You can sort of read 5890 right there, right? We have gases. We have both a carrier gas, right, which is helium, and a fuel gas for our detector, which is hydrogen, right? It's plumbed in through the back, but the injector port is on the top. This is where we will stick the micropipette syringe. The column is held in an oven, right? So the column is inside that oven, right? There's a control panel. The detector is right here in this region, right? Here's a flow meter so that you can calibrate the proper flow through the instrument, right? Ours doesn't have, right? Ours is set up, we do not have the flow meter constantly attached to the instrument. And then the output on these, right? We have an output like this. It's a thermal chart recorder instead of a computer output, right? But this looks just like ours. So the columns in older instruments were glass tubes that you would have to blow silica, sand, into, and then you would blow some kind of high molecular weight solvent through to coat that sand to create the non-polar stationary phase, right? They went to thinner metal tubes that still used coated silica. But current GCs, and the HP 5890 uses a glass capillary column, a very thin glass tube that's thin enough that it can be wrapped, right? These columns can be, up to 30 meters long. Ours, I think, is more like 10 meters. And then the coating, instead of being on particles, the coating is on the inside surface of that capillary, right? It is a waxy coating that creates a non-polar surface that the analytes, the materials being separated, can partition into, right? So here's a cutaway of one of those glass capillary columns, right? The fused silica, the blue, is actually the glass. They appear brown because they've got a plastic coating on the outside to protect them, to make them a little less brittle. And then the stationary phase is a non-polar coating on the inside of that fine glass capillary. Okay, so the blue here represents the glass walls of the capillary. Then it has a non-polar coating on the surface, the interior surface. This is the carrier gas moving through, probably helium. So when you inject the analyte, A is the analyte, into the carrier gas, as it enters the column, it tends to partition into the non-polar coating, right? But we are at a higher temperature, and so this has a substantial vapor pressure. And so it tries to establish an equilibrium between analyte in the coating and vapor above it. But as it evaporates into the column, the carrier gas moves it along. And then it reaches a new spot in the nonpolar coating where there's less analyte, and so it tries to partition back in. But that means, as this is moving, that means the concentration of analyte here is less again, and so analyte tries to evaporate. And so it tends to move through the column by evaporating, moving, and then partitioning back in. And then it evaporates, moves, and partitions back in. And so it tends to roll down the column like this, moving into the carrier gas, moving a little ways, partitioning back into the nonpolar phase. Well, right, the more volatile a material, and remember, volatile to a chemist means it has a higher vapor pressure, right? That's what chemists mean when they say volatile. Volatile refers to whether something has a vapor pressure, okay? Normally, a higher vapor pressure is related to a lower boiling point, right? So materials with higher vapor pressure, that is, usually materials with lower boiling points, they spend more time moving in the carrier gas, and so those move through the column faster. And so we can separate materials based on their volatility, that is, their vapor pressure at the increased temperature, right? The things with lower boiling points or higher vapor pressures move through the column faster. The things with higher boiling points, those have lower vapor pressure, they move through the column slower. And so we can separate on the basis of boiling point temperature. So this is a cartoon showing a mixture of analytes, right? They're injected, they're picked up by the carrier gas, they go into the column, right? And so it's a combination of affinity to the stationary phase and volatility. And most of the time, that volatility factor in gas chromatography is the basis of separation, okay? And so the more volatile components roll through faster, spend more time in the vapor phase, so they come out first. The less volatile components spend more time in the stationary phase, less time moving in the gas phase, so they move through more slowly. Then our question is, if these are all coming out in the gas, how do we detect them? There are a variety of ways, but I will tell you how our detector works. Our detector is a flame ionization detector, okay? As the gas is coming out of the column, we add hydrogen to that gas, and then we use a spark to ignite it. So this is representing, right, this is representing a hydrogen flame. Now, within that flame, ions are created as part of the combustion. And so that flame is between two electrical plates. And so we can measure the electrical conduction across those plates, right? There's a power supply. So we can measure the electrical conduction across those plates, right? And that current is measured by the detector, okay? Now, as long as there's no other material coming out of the column, the only thing causing ions in the flame is the hydrogen, and so there's a fairly low and constant conductivity. So the hydrogen flame creates the baseline, right? If organic materials come out of the column, when they burn, they increase the number of ions in the flame. As the number of ions in the flame increases, the current crossing this gap increases, and the detector registers that change in current and plots it, right, as a peak. And so we register the time since injection, right? And we can also measure the area of that peak, because the area is roughly proportional to the number of molecules that created that peak. Okay? So we can get a quantitative measurement, right? And we can use the characteristic time to, right? So it's a combination of time characteristics for the molecule to come out and the area that we can measure for each molecule. Okay? So we will use this, right? The time to determine which isomer is coming out, and the area under the curve to measure relatively how much of the isomer is exiting the column. And we will show you in lab how to actually run the GC and do the injection.